yeah. So whenever we are ready, then I will show the.
Okay, shall I?
Yeah. Okay, wait a minute. I wonder if Bu Aminah is already here or Pak Asep already here, the head of department. Yeah.
They must.
Okay, Pak Asep. Yeah, I think most of us are already here, Pak Asep.
Okay.
Yeah.
I'm sorry for the late because just a few minutes I finished the lecture. Shortened to become just 1 hour. Okay. Anyway, thank you. Good afternoon for Indonesian time. Good morning maybe for Professor Jason Lynam. Thank you everyone, especially for Professor Jason Lynam for today. We will be having public lecture or guest lecture delivered by Professor Jason Lynam entitled Shining a Light on Manganese-catalysed Reaction. To follow up after our virtual visit in early November for RSC accreditation. Okay, on behalf of the Department of Chemistry, we all really appreciate and give big thanks to the assessor of the RSC that finally we are accredited by RSC. So now we are among the, if I notice, among 440 study program and among 80 university that granted or accredited by RSC. And we are committed for the years to come until 5 years to maintain and develop and also improve our conduct in terms of the education for magister program in Department of Chemistry. Again, thank you and time back to the moderator. Terima kasih Bu Yuni.
Okay. Thank you very much, Dr. Asep Sefamila, our head of department. And now, Prof. Jason, do you mind if I read shortly, short CV of you that we found so far, so the students will know
Please,
the detail of yours. Okay, I will share the screen first, and then so everybody can see. Okay, let me see. Right. Okay. Oh, sorry. Okay. Good afternoon, everyone, mostly the students, and good morning, Professor Jason Lynam. Allow me as a moderator to read a very short CV, very brief CV of Prof. Jason Lynam. That Prof. Jason Lynam is Professor of Chemistry in University of York, and you can see the detail here. Yeah, and this is the career pathway so far that graduated BSc undergraduate degree in York University and also PhD with Dr. Roger Maybai from York University, and carry out postdoctoral position at Bath University with Professor Michael Green and Dr. Andy Burrows. And then I got also received Ramsay Memorial Fellowship from University of Bristol in the year 2000, and then appointed to a fixed-term lectureship in organic chemistry since 2002, and promoted to senior lecturer in 2010. And this is the publication. actually already published more than 150 articles and chapters focused on transition metals or organometallic chemistry for various applications such as catalysis, biochemistry, pharmacology, and including computational study. And also received a UKC GE recognized research supervisor in 2019, and recently also awarded grant for seeing the light with manganese, unveiling catalysis by an earth abundant metal by UK Research and Innovation recently this year, Prof. Jason, 2022, which
That's
is
right.
will be the main topic for his talk this afternoon. Okay, without further ado, the time is yours, Prof. Jason. You have about 40 minutes, if so,
Super.
to give your talk, and then after that, we will have a question and answer. Yeah, mostly from the students. We expect that more. You can ask a lot of questions to Professor Jason. Okay,
Great.
the time is yours. Yeah, I will stop sharing. Thank you.
Thank you. Here we go. Thank you. I'll just get my presentation up. There we go.
Yes, yeah.
Great. Can everybody see that okay?
Yes, yeah, it's good.
Super. And thank you very much for all of the kind words and the kind introduction. It was a real pleasure to meet most of you and colleagues during the recent accreditation visit, and I really enjoyed talking to you, talking to your students, and hearing about your courses and the chemistry that you're doing. And you know, really positive to hear about the outcome from the accreditation a couple of weeks ago. So yes, that was very you know, I was very happy to see all that and be involved in that, and hope you found it useful as well. And I guess you know, very happy as well to follow up and give you a little bit of a talk about the work that we've been doing recently in York on trying to understand the chemistry of manganese-catalysed reactions. So as was said in the introduction, my background is in organometallic chemistry and in catalysis. And what we've really been interested in doing about the past few years is thinking of ways that we can try and understand what is happening within a catalytic reaction, and trying to get direct experimental evidence for some of the very short-lived intermediates that are very important in catalysis. And just by way of introduction, the way that we might think about a transition metal catalyzed reaction, this is kind of a textbook picture for what we might actually see from a mechanism of a catalytic reaction where a transition metal is involved. And often what we'll see is a catalytic cycle, something that looks like this here. So we can imagine a hypothetical reaction where we have two substrates which I've notionally called A and B. We have a transition metal catalyst then that combines them to form a new bond. And you know, this might be something like a Suzuki reaction or something like that, for example. Now, the picture that we would normally have in for a reaction like this is that we will start off with our bench stable precatalyst. That's the material that we'd often have and weigh out in the laboratory. And in the vast majority of cases, these precatalysts undergo some kind of an activation process. And I've shown it here by loss of a ligand from the coordination sphere of the metal. And then that makes our active catalyst, which will interact with the different substrates of the reaction to activate them and then promote the formation of the bonds that are needed to make the product of the reaction before being recycled again. And of course, transition metals are really good at this sort of chemistry, really good at doing catalyzing the transformation of organic substrates, because for many reasons, and the two principal ones I always sort of come back to is that transition metals, particularly in low oxidation states, bind very strongly to organic compounds. And because transition metals can change oxidation state readily, they're very effective at shuttling electrons around. Hence, that's why they're able to do many of these catalytic reactions. Now, moving on from that kind of textbook picture of a catalytic cycle and catalytic reaction, perhaps a slightly more informative way to think about how a catalytic reaction functions is by considering a potential energy surface like this one I've shown here, where we essentially skip through the reaction starting from our activated catalyst here. It will then proceed through a series of different transition states, and intermediates as it works its way from starting material through to the product. And the energies that are shown on here, they're just notional. They're just to give an idea for the feel of how these reactions might work. And the way that a mechanistic chemist like me thinks about this is, if we're going to rationally improve how our catalyst works, if we know the structure of all of the intermediate and potentially all of the transition states in this reaction, then what we can do is think about rationally improving how the catalyst works and making sure that we can design the best catalyst for the best job. So how might we go about doing that? So there's a number of different experimental methods we can do to try and probe these reaction coordinates. So the first one is we can think about developing a structure-activity relationship. And this is a very traditional way where you might, for example, change the nature of a phosphine ligand in the coordination sphere of a metal and see how the changes to the electronic and steric parameters of the ligand affect the outcome of the reaction. We can also perform reaction kinetics and measure the rate of the reaction. And this will give us the free energy of activation for the reaction overall. And we can also perform in operando spectroscopy, where we can try and potentially observe any catalyst resting states or long-lived species, or potentially watch the product being formed in the reaction. And we can also try and find out what happens to the catalyst when the reaction is finished by trying to figure out how is the catalyst deactivated, and that will also tell us about the reaction. And then, of course, we can complement this with computational chemistry, mostly using density functional theory, which will allow us to calculate potential intermediates and pathways in the reaction. So, of course, experimentally, we're never going to observe this kind of a transition state in the condensed phase, but DFT will allow us to calculate what it's like. But there are a number of challenges here. And the principal ones is that if you have a good catalyst, what it means by definition is all of the intermediates that are involved in the reaction are going to be very, very short-lived, and therefore they're going to be present in low concentration. So our opportunity to actually observe them is going to be very, very difficult. And in addition, reaction kinetics can tell us about the height of the barrier here, but what it can't tell us about is the nature of individual states. So, for example, this state here, we're never going to be able to observe or get an idea about its reaction. So what we were trying to do is to develop a method using manganese chemistry, which I'll come on to in a moment, to try and understand and to observe all of the different minima, all of the different intermediates in a catalytic cycle. So it's a very ambitious goal that we've set ourselves. And what I'm going to tell you a little bit about how far we've got in trying to achieve that, but actually trying to observe these short-lived intermediates that are present in a catalytic reaction. And so our idea to do this goes back to this initial picture that we had right at the very start. And if we focused on this pre-catalyst activation step, where in most reactions you heat them up and which results in, for example, a ligand being dissociated. What we realized is that we could promote that same sort of process, that same chemical activation process of our pre-catalyst, but instead of using heat, we could use light. And so we would basically be able to simulate the way in which the pre-catalyst is activated using a source of light. And if we were to use laser light to do that, then we can control very, very carefully the timing at which the activation happens. And if we use one laser pulse to activate our compound, we can use a second laser pulse at a period of time later on to try and probe what has happened using a suitable spectroscopic method to the catalyst as it happens. And because we could, as I said earlier, we can very, very finely control the timing of these experiments, it should be possible to observe even the fastest events that underpin catalysis. And so we needed two things to be able to do this. We needed a catalyst system to study. And in addition to that, what we also needed was a spectroscopic method to do that. So in terms of the catalyst system that we studied, we'd actually been working on these molecules for a completely different application for many years. So these are manganese-1 compounds containing these cyclometylated nitrogen-based ligands here that have got 4 carbonyls. And while we were working on these compounds for a different application, a series of studies were published, pioneered by Konyang Wang, which showed that very, very similar catalysts based on these manganese bromide species here were able to catalyze the reactions I've drawn on this slide here, where you can take very, very similar sort of nitrogen-containing substrates with a carbon-hydrogen bond in this position, when what the manganese is able to do is selectively activate this CH bond here, and in the presence of a suitable unsaturated species such as an alkyne or an activated alkene, it's able to then form new carbon bonds, and in this in all of these reactions. So this is very attractive because it's doing the sort of chemistry you might associate with a rare platinum group metal like palladium or rhodium, but it's being done by an earth-abundant transition metal compound. And in addition to that, what was really important is these compounds that we've been looking at for a different application, both us and Konyang's group were able to show that these are actually pre-catalysts in their own right. So instead of using this brominated species, you can use this as a pre-catalyst, and it works in essentially the same way. And the mechanistic proposals that have been put forward to this are shown on this slide here. So if you had this brominated precursor, there was essentially 2 pathways that it could undergo. The first way is it could undergo the CH activation of this nitrogen-containing heterocycle to give those compounds I was talking about a moment or two ago. They could then lose carbon monoxide thermally, allowing the substrate, the second substrate, to coordinate to the manganese. And then there's a series of carbon-carbon bond formations that then lead to the formation of the product. And we were also able to show in a separate way that if you have a terminal alkyne here, then actually the manganese catalyst may function by first of all breaking the CH bond of the alkyne to give these alkynyl compounds, and then you actually end up in the same bit. Then the CH activation of the second substrate takes place, and you end up forming the same intermediate, but via a different mechanism. And what we're aware of is that we could make these compounds here, these pre-catalysts, by simply taking this well-known benzyl manganese pentacarbonyl compound and reacting it with 2-phenylpyridine, and you can basically prepare these as air and water stable materials on a 10-gram scale within a day. So there's a very easy access to these compounds. And what we did in a series of studies was, first of all, of course, as I mentioned earlier, show that these compounds here were pre-catalysts in their own right. And then we did some NMR studies where we were able to show that an analogous compound here, where the phenol group has been substituted by this pyrone functionality, if we're able to photolyze that at low temperature, we were able to observe some of the intermediates that were involved in this reaction. So this species were a bit of feedback there, I think, of this carbon-carbon bond had been formed. We were able to identify by NMR spectroscopy and show that under the right conditions, going back through to the product. But this sort of illustrated the key point I was saying. The proposed intermediate in this reaction would be this species here, and it was simply too short-lived to be observed even at 240 K. It was so very short-lived that we just simply couldn't observe it. And this tells us that even when using techniques like NMR, there's lots of detail, lots of short-lived species that you can't observe because the timescale for the NMR experiment was too slow. So before I get on to some more of the results, this is the experimental method that we've then been using to try and answer these problems. And this is a technique called Timeresolved multiple probe spectroscopy, which is based at the Rutherford Appleton lab in the south of England near Oxford. And the way that this sort of functions is that you take a laser and you take the beam and you split it into three different components. We use these devices called optical parametric amplifiers, which essentially tune the laser beam to the frequency that we want. And that we take some of the beam and we use this as what's called the pump. And this is the laser light that activates our manganese compound. And that results in the loss of one of the 4 carbonyl ligands, the one I've highlighted in blue here. And that's normally at 355 nanometers. We then follow that with a second probe beam in the infrared region of the spectrum that allows us to then identify what's happened to the vibrational modes of the remaining carbonyl ligands across here. So we'll be able to probe the nature of what's happened to the metal by observing the vibrational modes in the infrared spectrum of these three CO groups that are remaining. And basically, the nature and the position of those bands will tell us about what is happening to the manganese during the reaction and also tell us about the kinetics. And when we do these experiments, we simply dissolve our compound in the appropriate solution and we flow it through an infrared cell where the laser beam passes through, because of course, each time we hit it with a laser shot, we destroy some of the sample because this process is irreversible. So we have to make sure there's fresh sample in the cell for every shot that we do. So we simply flow it around this system here. And then, and so essentially by using this pump probe technique, we can sort of study what happens. Now, pump probe spectroscopy has been used by many people for many years before. But what's really special about the piece of equipment at the Rutherford Appleton lab that we use is because of this time-resolved multiple probe spectroscopy method, is we give it one laser pulse to activate it, and they're separated by a millisecond. But then what we do is give it lots of probe pulses, all of which sit at a time distance away from each other of 10 microseconds. And then each one, although it's 10 microseconds apart from the one that follows, we can vary the delay from where it starts with respect to the initial pump by anything from 1 picosecond up to that 10 microsecond delay. And the overall take-home message from this is that because of the way that this is working with the pump and the probe laser beams in working in a synchronized fashion, that we can record time-resolved spectra on a delay from about 0.5 picosecond up to about 1 millisecond in time. So we can look at reactions that are occurring here over essentially 9 orders of magnitude of time, from very, very fast to relatively, from our perspective, slow events. So we can start to see a whole variety of different chemical behavior. And so just going back to the global picture before I show you some results, this is the reaction that we're going to focus on that I talked about earlier, catalyzed by these manganese cycles. And the idea is that we use one laser pulse, I've said, to activate the compound, and then a second laser pulse at a defined point later to study what's happened on the base of the 3 remaining CO ligands. And when we think about our catalytic reaction, it's clear that there's quite a lot of components in there, all of which can potentially activate with the activated precatalyst. So there's the solvent, there's the alkyne, there's the 2-phenylpyridine, and then of course, how do they work when they're all together? And can we deconvolute how all this works? So I'm basically going to tell you now about how all of those different components interact with the reaction, and you can then sort of see how we can build up a picture of what's actually going on in a catalytic reaction using this method. And so the data that I'm going to show you are all going to look broadly like this, and these are different infrared spectra for the compound that we're looking at. So when you see a negative peak, that is something that has been lost when, after the laser pulse has arrived. And in every single example I'm going to show you today, the negative peaks correspond to the ground state infrared spectrum of the starting compound, because that has been lost when it's hit by the laser. The positive peaks are then sometimes called the transient peaks. These correspond to the products that are arising as the reaction evolves with time. And by analysis of these product peaks here, that can tell us a lot about what's happening in the reaction. And just one minor point I'm going to make is actually a lot of the time I'm going to tell you that this is what we've made. A lot of the work that we do here corresponds to trying to do the control experiments to demonstrate unambiguously the nature of the species that we make, some of which only live for a handful of picoseconds. And what we have to do is try and piece together experimental information from control reactions and also from using calculations with density functional theory so that we can understand and make the spectroscopic assignments that we make. I'm happy to talk in more detail about that, but obviously it takes, there's quite a lot of the work goes on in the background to making those assignments. So in this experiment here, all that we've done is photolyzed our starting compound in acetonitrile as the solvent. And what we can see that when the spectra, if we look at the resulting spectra, negative peak shows that compound 1 has been lost. And we see two major positive peaks here, a sharp feature at this position and a broader position here. What that tells us is that we've then formed a compound with a pseudo C3V geometry, and that we've lost one of the carbonyl ligands that was mutually trans to one another. And then we've made this species here with three mutually cis carbonyls and an acetonitrile bound into the vacant coordination site here. And we can see some other peaks here that I can talk about if necessary. These are assigned to actually an excited state, the triplet excited state of compound 1. But the major photoproduct is this species as shown here, where we've lost the CO and replaced it by the solvent. Bearing in mind that this is formed within about 2 to 4 picoseconds, it still actually means that even on this time scale that we don't see an intermediate which doesn't have the solvent bound. That is still too quick and too short-lived to be observed even on these experiments. And we can see that when we change the nature of the solvent, we see a difference in the change of behavior. We can see this is in heptane solution, and we can see now our bands are much sharper because there's less interaction between the solvent and the compound. And what we're able to demonstrate is that in this case, the heptane binds to the manganese through one of the carbon-hydrogen bonds, or that's what we propose is taking place, is that we have a so-called sigma complex in which the heptane is bound. And an important point here is that what we can see is that the position of the product peaks in the infrared spectra shift on when we do the experiment in heptane or in acetonitrile, which is telling us that they're sensitive to the nature of the compound that's bound into this site here, where the CO that has been lost was. So we can use them to tell us about what's taking place in our catalyst. And then, for example, of how we can use that is when we look in using THF as the solvent. When we use THF as the solvent, we actually see some behavior which we weren't expecting to see. The initial formed product has got a peak here and a peak in this position here. And when we look at the frequencies, the wave number bands of those peaks, they're essentially the same as they were when we saw the experiment done in heptane. And so the argument that we then make is that if the band positions are about the same, then the solvent must be bound in about the same way, because that's what's essentially present in the coordination sphere of the manganese. And so what we proposed is that the initial form species, where I've got these bands highlighted here, the heptane just simply, the THF binds through one of its carbon-hydrogen bonds. Now that's very short-lived. It lives for about 50 picoseconds before isomerizing, as I've shown in this diagram here, to perhaps what we might have expected with the oxygen being bound to the manganese. And this is more similar to the acetonitrile case. And when we look at the kinetics of that, we can see that the lifetime of this process, as I said, is about 20 picoseconds for the loss of this species here and the growth of this compound here. And the way to visualize this is that why does it do this in the first place? Well, on these time scales, what's taking place is the manganese has lost the carbon monoxide ligand and essentially it coordinates to the nearest pair of electrons that it can get. And in this case, it's in this carbon-hydrogen bond before it then isomerizes to the most thermodynamically preferred binding mode of the THF, as I've shown in this position here. So you can see, using this method, we can get insight into the dynamics of the solvent. But perhaps more exciting, what happens when we add the substrate? What happens when we add the phenylacetylene, which is vital to the reaction that we're trying to understand? In our first experiments, what we did was simply to take our precatalyst and then dissolve it in neat phenylacetylene. And we're able to do this because a key property of this material here is that it's extremely stable as long as you keep it in the dark. So you can dissolve this in all sorts of media and actually it won't actually change until you start to irradiate it. And what we see in this experiment when we photolyze it is at very short times, we see something that's really unexpected. The phenylacetylene binds through its arene group, first of all, and we were able to show that by looking at a reference spectrum of when we did an experiment in toluene. Then it isomerizes, similar to what we saw for the THF, to a more thermodynamically preferred binding mode, where it's bound through the alkyne group in a classical E2 fashion to the manganese. And we can see that because of the shift in the infrared band positions of compound B, where the bands for the carbonyls move to higher energy. That's because our alkyne is a good pi acceptor ligand, so it's competing with the carbonyls for the electron density of the manganese. And so therefore there's less pi back bonding to the carbonyl antibonding orbitals, and therefore the CO bonds get stronger. And we can see that sort of being in the band positions that we see here. And then we see a final product being formed on a longer time scale over 50 microseconds. And what's taking place here is this is actually the carbon-carbon bond formation occurring between this ligand and this ligand here. This is the crucial CC bond activation that takes place when we do the catalysis, and we can analyze the kinetics of that reaction, and so therefore we are seeing carbon-carbon bond formation taking place in real time in these experiments. And we're able to develop this method further by, instead of just doing it in neat phenylacetylene, to then try and mimic what happens more under the catalytic conditions. And in this case, we have a toluene solution of phenylacetylene. And in this instance, what we see is there's the reference spectrum of toluene on its own. At early times, what happens is all the compound does is bind initially to the toluene, because there's much more toluene in the reaction than there is phenylacetylene. Then what we see after we form compound D is it then goes through with the alkyne binding to the manganese to form the species that we saw on the previous slide, compound B, as shown here. And we can see this in the kinetics of the formation of compound B. So here what we see is the substitution of the toluene by the phenylacetylene before it decays away as it undergoes the same carbon-carbon bond formation that we saw on the previous slide to give an essentially identical spectrum to what we saw before. And then we're able to do a really nice bit of what I would call sort of undergraduate kind of kinetic experiments by working under pseudo first order conditions, where we essentially kept the concentration of phenylacetylene high, but we varied it systematically as shown along the bottom here. And we were then able to measure the observed first order rate constants for the formation of D through to B, and then from B through to C, as shown from that step and that step. And what we're able to show when we analyze those rate constants was that if we looked at the conversion of D to B, that's this red line here, then this showed a linear relationship with the added phenylacetylene concentration, indicating this was a second order process, and we're able to determine from the gradient of this plot the second order rate constant for the substitution of the toluene, as shown here. But then the conversion of B to C, and that makes sense, right? Because of course we've got the phenylacetylene and the complex coming together, which means that would be consistent with it being a second order process. But then B to C, as drawn, is intramolecular and should have no dependence on the addition of extra phenylacetylene. And you can see that's the black line here, where all of the rate constants obtained were identical, regardless of the concentration of phenylacetylene. So that tells us that K2, this is a first order process with that rate constant there. And what we were then able to do is extend this study by looking at the effects of all of the different components on the reaction to try and understand what was controlling the carbon-carbon bond formation that was underpinning this reaction. And we did this in two ways. In the first instance, what we did was change the nature of the group that was bound to the manganese in the starting complex. And so we had this indole-based substrate, the compound you've seen previously, through to ones containing a benzophenone or an imine, a pyrone or a pyridinone group. And on the bottom here, this is the rate constant for the carbon-carbon bond formation for each of these particular substrates. And this is a logarithmic scale. And you can see that actually there's a wide variety in difference in behavior. This compound here is very, very slow, whereas this one here is it's 2 orders of magnitude faster. So the nature of the group that's coordinated to the manganese does play a role, although you can see compounds 2, 3, and 4, where in all of those cases, it's a phenyl group that's involved in the carbon-carbon bond formation. They all fall in a very narrow range. But when we make bigger structural changes, then there's a bigger effect. And then what we did was study the effect of changing the alkyne on this, on the rate of this, the rate constant for this reaction. And what we found, again, a logarithmic scale at the bottom, we found that if we have electron withdrawing substituents on our alkyne, then the reaction is accelerated. It's much faster compared to electron donating substituents. And if we increase the steric bulk on the alkyne, then we also slow the reaction down. And actually, when we have a long chain hydrocarbon one here, this is Dec5-ine, then actually the rate of the insertion reaction was too slow for us to observe in that particular case. And so having got all of those data together, what we wanted to do was try and understand then the factors controlling the carbon-carbon bond formation. And to do this, we turned to density functional theory. And what we did was, first of all, calculate for all of the examples I've shown you on the previous slide, the transition state for the formation of the carbon-carbon bond. And so going from the alkyne complex through to this seven-membered manganocycle through this transition state. And in this graph here, what I've got along the bottom is our experimentally determined free energy of activation. And then on the y-axis, there's the calculated value from the DFT. And of course, although the absolute values are not going to agree explicitly, what we can see is that there is a direct correlation between the experimental data and that calculated by theory, giving us good confidence that the theoretical model was sound. And what we then did was analyze the resulting orbitals and the resulting in the transition state to try and understand what was the electronic basis of the factors controlling the rate of the carbon-carbon bond formation. And to do that, we turned to a technique called MBO, natural bond order analysis. And what happens in this is it distills down the kind of molecular orbital picture that you might be familiar with. It distills it into a more chemical, intuitive way of looking at the bonding. And in particular, from these systems, we're able to look at the donor and acceptor interactions within the coordination sphere of the manganese. And the take-home message was this. This is the carbon-carbon bond being formed in the transition state. And the key interactions that were controlling this reaction when we analyzed it across all the structure was that this is the two electrons in the carbon-carbon bond that's being formed. And they're involved in they're able then to be donated to a vacant metal d orbital, as shown in this interaction here. And at the same time, what we were able to identify was there was a filled d orbital on the manganese, which is involved in donating its electron density back to the sigma star orbital on that carbon-carbon bond that's being formed. And of course, this is essentially identical to the kind of synergic interactions that you might expect to see in transition metal, low oxidation state transition metal compounds with ligands like hydrogen and ethene and carbon monoxide. And in addition, we were also able to see a third interaction where there was donation from a lone pair on this carbon atom into that same sigma star orbital on the newly formed carbon-carbon bond. And what we're able to show is it was the strength of these interactions which was correlating with the rate of the insertion. And that the stronger these interactions, the stronger the donation and the acceptor interactions were, the faster the rate of the CC bond formation was taking place. And it kind of makes sense then that we can relate that back, for example, to the properties of the alkyne. Because if the alkyne is more bulky, then it's going to be further away from the metal because of steric constraints, and therefore the orbital overlap in these interactions is not going to be as strong. Conversely, if we have an electron withdrawing group on the alkyne, then that's going to make it a much better acceptor ligand, and that's then going to promote this interaction here. And so this sort of picture of what's controlling the CC bond formation is able to sort of give a global picture of how these reactions work and what are the factors controlling CC bond formation. So what I'm going to do, just to sort of finish off in the last few minutes, is show how we've taken this idea and then extrapolate it to try and understand again what's going on in the catalytic reactions. Because so far we've looked at two components. We've looked at what happens when we've got the solvent present, and we've looked at what happens when we have the alkyne present. But what happens when we start to think about looking at real catalytic reactions? When, for example, we've got different substrates that are present as well as both the alkyne. And of course, the one that's used in this catalytic reaction is 2-phenylpyridine. And so when we have a mixture of those components in the reaction, what we're able to show is that if we photolyze this, we get initial formation of the toluene complex. So the toluene binds first of all. Again, that makes sense. There's more toluene in the reaction than anything else. This is a kinetically controlled coordination. But then what happens is the toluene is substituted by both the 2-phenylpyridine to give compound E, as I've shown it here, but also then by the alkyne to give compound B that we've seen previously. And we can see this, the blue diamonds here, we can see are identical to a reaction that's just performed with 2-phenylpyridine on its own. Crucially, what we then saw in this experiment was compound E did not change for the rest of the experiment. That just sat and looked at us. Whereas compound B was then able to undergo the same carbon-carbon bond formation in this particular set of substrates. And the rate of insertion is very, very similar to that we saw previously. And the important take-home message from this is that often we draw these catalytic reactions as if they're working like clockwork. But actually what it shows is that after that initial pre-catalytic activation, about half of the manganese is actually no longer in a position to perform catalysis. It's only compound B that's going to be responsible for the productive catalysis. If compound E is going to enter the catalytic cycle, we have to wait for this 2-phenylpyridine to be lost from the metal and be substituted by the alkyne, which is going to be much, much slower than this step here, B through to C. So it tells us about what's happening to the fate of the manganese catalyst when it's going on these initial fast times. Now, having shown that we could use light to promote these reactions, we then fancied that we could possibly develop a new photochemical route to do the catalytic reactions that are normally done at about 100 degrees in a N-butyl ether. To cut a long story very short, our idea doesn't work, but we were able to discover something else instead. So what we screened was taking compound 1 and photolyzing it with our phenylacetylene in the presence of various different additives and of course some of the 2-phenylpyridine. And we just photolyzed this with an LED, and we were trying to make this this compound here. Now, the best conditions we were able to find was that after 48 hours of photolysis, in the presence of benzoic acid, we're able to get 81% conversion of compound 1. So this was not catalytic, this was stoichiometric to form this species here. And we could not get it to work in a catalytic sense. And we did a couple of control reactions. So if we just did it with 2-phenylpyridine and the phenylacetylene, got no conversion. And if we did this reaction in the absence of the light, again, there was no conversion again. And that's what we expect. We know compound 1 is thermally stable. It's only activated either on very strong heating or on photolysis. But what did take our eye is the difference between entry number 1, where we didn't have a carboxylic acid added, and then all of the other cases where the reaction was successful, where we added, for example, benzoic acid. And what this was telling us is that clearly the carboxylic acid must be having a really important, playing a really important role in this reaction. And so we once again went back to doing our time-resolved experiments to try and understand how this was working. And what we found, because compound 1 is so stable, we could dissolve it in nitacetic acid. And so by taking compound 1 and dissolving it in nitacetic acid, what we're able to see was some really quite remarkable transformations taking place. In the first instance, what we're able to see was that the acetic acid bound in a pretty random way, probably through this carbon-hydrogen bond through to the manganese. That's this spectrum here. Before it then rearranged to a perhaps more typical binding mode that you might expect, with the oxygen then coordinating in with the species shown with the black squares. What we were then able to see was compound H, where the OH group had rearranged and was now involved in an interaction here I've shown as kind of a hydrogen bond with the phenyl group of this ligand here. This is the species with the triangles. Before then, there was the protonation. The proton was transferred onto the ligand to give us compound I, as shown with the red dots here. And we're able to measure a kinetic isotope effect for this, for H going through to I of 5.7, confirming that at least in this step, there must be a hydrogen or a deuterium transfer that's taking place. And what was really quite, what we was really happy about in this particular case was this sort of transformation here. If we go backwards, what's happening is the carboxylate group, if we think about reversing this process, is deprotonating the substrate. And there's been a huge amount of work done to show how carboxylate groups are vital additives in CH bond functionalization reactions. And computational work, not by others, but primarily by Stuart McGregor at Heriot-Watt University, and showed that these kind of intermediates were were predicted on the basis of the calculations to be key steps in these reactions. And what our technique allows us to do, because of the fast time scale and the robustness of compound 1, it allowed us to actually unearth and directly observe these states. And so this is perhaps the final results slide I'll show you for today before I just obviously thank everybody who's been involved in the project. And this is to show you about as far out as we can go in studying step-by-step reactions underpinning catalytic reactions. And so in this particular instance, what we have is a toluene solution of our compound, our alkyne, and a carboxylic acid added to it. And what we're able to observe, if we look at the spectra over here, is the step-by-step formation on a picosecond time scale, the formation of compound D, the substitution of the toluene by the alkyne to give alkyne compound that we've seen before. Then, all in the same experiment, we're able to see the CC bond formation taking place on a microsecond time scale. And then the slowest event is the protonation of the manganese carbon bond, as shown here, to give compound J, in which we've got the product then bound through to the manganese. And this is taking place over 300 microseconds. And once again, we can analyze the kinetics of this process, and we can see that for now which step we're looking at here. So in looking at steps, this step here, this line here shows us that if we change the concentration of phenylacetylene, the rate constant for this reaction isn't changed. But if we change the concentration of the carboxylic acid, then it actually is. Again, consistent with the fact that this step involves protonation by the acetic acid. And so just in lieu of time, I'll just skip through this last bit. But what I want to sort of just conclude for you is just show is the kind of my take-home message from all of this is using this Trump's method has really, so the time-resolved multiple probe spectroscopy method. What it means is that by using light to simulate how the manganese catalysts are activated, it means that we can see a whole host of different things that are taking place in the catalytic reaction that we're essentially blind to. So things like understanding excited states that are formed, understanding solvent binding and ligand binding, and then how they rearrange in a very fast time scale. On a nanosecond time scale, we can start to see how those ligands then undergo, the solvents undergo substitution. But then on the longer microsecond timescales, we can see things like carbon-carbon bond formation taking place. And as we go out to 300, 400 microseconds, we can then see the formation of the metal-bound product. So really starting to understand and directly observe what's taking place in these metal catalyzed reactions. And as you might imagine, all the work I've shown you today has involved a big bunch of a big team to try and make all this happen, not just me. So first and foremost, I want to thank my colleague in York, Ian Fairlamb. This has been a collaboration with him and his research group over about the past 5 or 6 years. And then also my colleagues Alison Parkin and Anna McClare have also made contributions to this work as well. And of course, I have to pay tribute to the PhD students who've all contributed to this work. So here's Ben Olcott, he's one of the people who started off the very initial studies I told you about. And then here we have, this is obviously me, this is Ian, this is the lifetime spectrometer I was telling you about earlier. There's our sample, and here's the laser table. This is Jonathan Eastwood and Anders Hammerback. And over here is Thomas Burden, all of whom are PhD students who worked on the project. The experiment is run by the so-called Ultra facility, and I've got to thank Mike Towering, Greg Greetham, and all of the team who've basically enabled us to do the spectroscopic measurements that we've been interested in. This work has been sponsored by a number of different funding bodies, including Syngenta, and Alan Robinson and Jean-Philippe Krieger have basically been extremely great people to work with, as they've enabled us to do academic work while thinking about the industrial applications. And we've had funding from these funding bodies as well. And just as a final point, this work, we were awarded the Royal Society of Chemistry Horizon Prize for this work. And what was really special to me about this award is it doesn't just come to the principal investigator. It goes to everybody who's been involved in the project, because research projects of this type take a huge team effort, and acknowledging that it's the team who's delivered on it, not just the PI, not just the, it's all of these people have contributed to this work. And I want to thank them in particular thank the RSC for the award of the prize, but and that team in particular. And just very, very quickly, just tell you a little bit, York doesn't look like this at the moment. It's covered in frost because it's about -9 here. It was overnight. So, well, obviously York is in the north of the UK. We're situated here about halfway between Edinburgh and London. And if any of you know anything about York, it's very famous as a medieval city. The entire place is dominated by this minster, the York Minster was built in the 1400s, and the entire city is still surrounded by the walls that were built in medieval times. This street here is the Shambles, which is now world famous because allegedly this is what J.K. Rowling based Diagon Alley on in the Harry Potter books, just the way it looks there, and is now dominated entirely by Harry Potter shops and very little else. And the university, we're based on a campus about 2 or 3 miles out of the city centre. This is a 16th century Heslington Hall. That's where the university administration is based. And our chemistry department, we're based in this building, the Dorothy Hodgkin building, which is very recently built, and our labs are just on the corner here. So I just want to go back to, once again, I want to thank all the people who've been in the project, and I also again want to thank you again for the opportunity to speak today. It's really good to see people following on from the accreditation visit, and I'm very, very happy to answer any questions that anybody may have. Thank you.
Okay, thank you very much, Prof. Jason. Please give a virtual or round of applause to Prof. Jason before we start the session for question and answer. Yeah, it's very interesting talk, really, yes. Because if I try to summarize what you have given just now, that it's really that, yeah, finally, yeah, we can see even though it's only in like a few seconds that the intermediate, and then where the what the transition of the before transition compound before to get the product that sit in or on the manganese catalyst. Yeah, it is. Yeah. Okay. I think now is time for the students to give a question. We can have probably like 3 students. You can raise hand, or I think we have plenty of time now. You can also, yeah, just raise hand and then I will try to catch who want to ask question. Okay, everybody. I think this is not just inorganic chemistry, but also organic chemistry. Yeah, the combination of this, because the compound itself is organic, right? Yeah, it's organic compound.
I often joke it's at the triple point of chemistry, because we have organic chemistry for the catalysis, inorganic chemistry, and then physical chemistry for the spectroscopy.
Yes, yeah, for the spectroscopy.
We have all those things coming together. Yes.
All right. Yeah. So it's like a kind of multidiscipline in chemistry somehow. Yeah. Okay. So anybody want to ask question? Hello, Prof. Bakri. Yes, please.
Hey, how are you?
Morning, Prof. Lynam. Lynam? Or
Lynam, yeah.
Lynam, right. Okay, good morning.
Morning.
Yeah, we are in the same position. It's very cold now.
Yeah.
So you can see my...
I can, yes.
Yeah. And again, is there any special energy for LED that you use? I mean, is it sometimes you get 1 watt and whatever, 2 watt and something like that?
Oh, yeah. There's two kind of answers to that question. So the obviously we use 355 nanometers as the wavelength, as the pump wavelength, but the laser energy I think is about 500 nanojoules. So it's not very, the overall energy is very small, but it's focused down into a very, very small spot. So we're getting a lot of energy in a very, very small piece of the sample.
Then again, can we use in another transition metal, for example, like cobalt or nickel?
So yes, and we've done some work with iron. We've done some other work as well with iron, and in principle, and actually there's been work done related to as even without transition metals, looking at the photochemistry, and actually we've done some palladium as well. But the crucial factor that we need for this to work is two things. First of all, the compound has to absorb light, and it has to be activated by the light. That's the first thing. And the second thing is we need a suitable probe source so that we can study what's happened to it at the end. So these compounds are great, of course, because we've got carbonyl ligands. They give very strong responses in the infrared. But there are other functional groups that could be used to probe that. And in addition, you could use electronic spectroscopy as well to look at it as well. So in principle, as long as you've got something that can be activated by the light, and then also a way to study what's happened to it afterwards, I think there's a huge amount of different systems we could look at.
Yeah, actually, I got another 2 questions. First, there's was it the catalyst manganese that's very crowded with the ligand, right? And how you solve the substrates connected to the metal? And do you know how long the bonding is?
In which, yeah, I mean, because manganese is quite small, you're absolutely right. It does make it very, very crowded. And normally we're looking about manganese carbon bond lengths, about 1.9 angstroms, something like that. And to the nitrogen, just a bit longer, I think, in some of the bulky cases. But yeah, I mean, it is quite crowded, particularly around when you've got two phenyl pyridines in there. Yeah.
Right. One more, I think it's in what we call it in slide number 22 or 23. It's a toluene. Take only 3 hours, is it? And
this one, yeah.
Yeah. The other one is 48 hours, number 4 and number 6, right?
Yeah.
So what's happened between both of them?
The reaction isn't going very well. Sorry.
It's quite interesting in the toluene. It only took 3 hours, right?
Yeah, so 3 hours between toluene and butyl ether, it's about the same. But you're right, it really does slow down at the end. And you often see this with photochemical reactions in that the conversion can sometimes go so far and then really slow down and stop. And the reason that that happens a lot is that sometimes what happens is that the products that you make on photolysis absorb more of the light than the starting material. And so it's sometimes called internal filtering. So what happens is that compound one is at the start is the only thing there, it's absorbing all of the light. But then all of the photo products that you make that build up with time, they then start to harvest more and more of the photons that are going in, and your reactions essentially plateau and then stop. And it's actually one of the problems with photochemistry in general, is that if your photo products absorb very well, then you can't drive it's very difficult to drive reactions to completion.
Right, thank you very much, Prof. Lynam.
You're welcome.
I've been to York. It's quite nice city, right? Thank you very much. It's interesting.
Yeah, thank you.
Makasih Bu Yuni.
Ya, sama-sama, Prof. Bakri. Okay, so please, anyone else want to ask question? Yeah. Oh, okay. Pak Iman Abdullah, please. Yeah. After that, then Zulkarnain, yeah. Okay. Wah. Now it's warming up. Everybody is getting eager to ask question. Okay, Pak Iman, please.
Yeah. Thank you very much, Bu Yuni, and thank you very much, Prof. Jason, for your nice presentation. So I have a question regarding the effect of alkyne substituents on the insertion reaction. So you mentioned that there are some effect of the substituents to the reaction rate. So I just want to know, what if the internal alkyne used has two substituents that are both electron withdrawing groups? So how does it affect the reaction rate? So that's my question. Thank you.
So I don't have it. We've never done that experiment.
Okay.
Okay. So I'm slightly going to have to speculate a little bit in that. So I think we basically have these two effects that are pulling against each other. You're quite right in that the internal alkynes are going to be that little bit further away, and that's then going to inhibit this interaction. The electron withdrawing effects, as we've already shown on the terminal alkynes, they counteract it a little bit. And so without actually having any experimental evidence, I think we'd probably be looking at, it'll just basically be how far along that continuum that you actually end up being. And I think actually there's a little bit more to the electron withdrawing, electron donating things as well, because I think what they may be doing is that if you make the alkyne a better pi acceptor by having a better electron withdrawing group on there, you actually bring it closer to the metal as well. And so all of this, I think, is all about how close the alkyne can get to the metal in that initial interaction. And so I would expect that we should actually just do it and measure it, but we've never measured it. But I think the two would compete against each other. That's a good question. Yeah.
Okay. Thank you, Prof. Jason. Thank you, Bu Yuni.
Okay, thank you, Pak Iman. Okay, here there's another question. Zulkarnain, do you want to ask the question by yourself? Please do. Yeah, just open your mic and just ask directly to Prof. Jason. Okay then. Yeah, maybe the connection is not good. So here the question from Zulkarnain. He really wants you to show again the setup of the equipment. It is the one that with the VR Google or like or this, I mean, okay, this one and also, yeah, which one of this? Oh, this one, yeah. Oh, looks very cool. Yeah, right. This is this is because for the safety or
yes,
because
it
it's
is
infrared.
Yeah, it's actually because the pump wavelength is in the UV region. And essentially, yeah. So you can, I don't know how well you can see this here, but the laser's basically being bounced around. So the sample is here and the laser's coming around the thing here. Now, in principle, it should be completely safe because, of course, the laser's directed by all the mirrors. But we wear the glasses because if there was a piece of stray light or the laser beam got misdirected, and then it goes into your eyes, then you could, in principle, your eye could get damaged. So that you,
okay.
so when you walk in there, it's actually really funny because the goggles have got everything you see is orange because of the filters, and then when you switch the laser off and take the goggles, it's like that. So yeah, so that's why we wear the laser goggles, is essentially to protect us.
And you have this in your lab, or you said it mentioned somewhere nearby Oxford?
Yeah, so this
that
is
you
in
said?
Oxford. This is a national
This is
facility.
the national facilities. Yeah. Okay.
We have access to that for
Yeah.
we have 5 weeks access a year to that.
Wow. All right. Okay. But Julkana, do you want to see this one, or actually you want to see the scheme of the setup? Yeah, because or this one that you want to see. Which one that you really want to make clear? I think you really want to see the one with the actual one. Yeah, what kind of experiment setup that you have? Yeah. Okay. So okay, thank you. And there's other question. Okay, if not, then maybe I think. Oh, all right. Okay, Bu Amina, please. Yes.
Thank you, Bu Yuni. Maybe I will add a little bit the question delivered by Prof. Bakri, because I am still curious regarding the manganese you use for your experiments as a catalyst. I'm still curious, what is the unique things of the manganese you use for these experiments? I mean, what is the benefit compared to other metals, that why you choose specifically for manganese? That is my first question. And the second question is in your experiments, mostly you have used the irradiation light, like 355 nanometer. What things should be considered for the irradiations?
Yeah, okay. So I'll answer the manganese one first. Actually, I'll go back a couple bits first of all. So why study the manganese, and what properties does it bring?
Yes.
So as I kind of indicated here, these kind of reactions, manganese is not the first element to be able to do these reactions by any stretch of the imagination. That doing it with, for example, palladium or something, or platinum, their example, and rhodium has been done before. And our argument for why study manganese is that manganese costs a tiny fraction of the cost of palladium and those other metals. So that's why we'd want to be able to do it. The problem is, and I didn't really go into this in too much detail, is that if you look at the catalyst loadings and the performance of the manganese catalysts, they're nowhere near as good as the precious metal. So we want to try and understand how they work. Why do these systems work so well? And I think one of the, I can keep flicking through slides, but fundamentally what's happening is, if you look at the mechanism, there's actually no change in oxidation state of the manganese through the entire reaction. It stays at manganese 1 all the way through. And that's a bit odd for a 3D metal, because they're normally easier. They normally get involved in redox chemistry more readily than the 4D and the 5D metals. But because you've got the carbonyl ligands on there, it gives you a very, very strong ligand field. And if it gives you that strong ligand field, it means you're not going to get it involved in redox chemistry. And I think that's what makes these catalyst systems so very, very special in terms of why they can't do it. Why 355 nanometers? Right, that's a really good question, which I might have an answer to. Sorry. Yeah, right. So the compound absorbs at 355 nanometers. Obviously, it has to, otherwise the experiment wouldn't work. And when we look at the UV vis spectrum, we can see that that's where one of the main peaks in the spectrum for the compound is. And when we then look at the orbitals that are involved, what we can see is that the transition that we're pumping at 355 nanometers, it's got both metal and ligand character in it, but fundamentally it results in CO dissociation. And that's why it's crucial for us. So when you're devising your sort of experiment to do, the way that you would do this is that you would look at the UV vis spectrum of the compound that you've got. That tells you the energy that you can photolyze at, and therefore which experiment you get, which wavelength to pick to photonize at.
Okay. Thank you very much for your.
Thank you. That's great.
Okay. Okay. There's any other question? Okay. If not, while waiting for the more question, I will ask you, Jason, about the spectroscopy side of this experiment. Yeah. I just wonder this. You said that you use infrared laser, to probe. Then does it mean that the mechanism actually it's similar to typical infrared spectroscopy, like the vibration of the molecule? Okay.
So that's actually a really good question that I didn't really make a point of.
Yeah, because maybe the students a bit confused because
No,
it
that's
is
fine.
like advanced.
So what we're actually doing is recording a normal infrared, normal transition mode. It's not FTIR, it's transmission mode infrared. So it's not an FTIR, but it's transmission mode. But that side of it, the infrared spectra that we get out, is essentially, is essentially identical to what we've to what you would do in a normal FTIR, in a normal transmission mode IR experiment.
Okay.
The only real difference is that we've obviously got we're making sure the timing works with the initial activation laser, okay, and that when after that we look at the different spectrum, because actually we only photonize a tiny amount of the sample, and so we have to look at what's changed rather than the absolute spectrum. But the principle of how it works, the principle of where the bands come, the selection rules, they're identical to normal IR.
Okay. Okay. So the basic is that. All right. Okay. And then about this the spectra. Sometimes you see it's very sharp one. You said that because there's no interaction with the with solvent, but then when it is the interaction with solvent, it become like a broader. You said it's a broad spectra. I just wonder. Do you mind if you explain that? Why when with the interaction with the solvent, it's become broad like that? Do you also see the shift of the peak of the interaction because of that interaction?
So the shifts are normally quite small. The shift in the ground state, the solvatochromic shifts in the ground state are normally quite small. But what the reason it gets broader is if there's very little, if there's, let's take the case, there's little interaction between the solvent and the complex. If it's very, very small, then essentially the vibrational energies are all going to be very, very they're all going to be fixed at one particular wave, at one particular energy. If, however, there's lots of different solvent interactions and very strong solvent interactions, then you actually get a spread of different energies within the band. You get a spread of different energies, and so you see it broadening out. So it looks a little bit broader like that. Okay.
And then, but then because this the manganese is with carbonyl ligands. The manganese carbonyl ligands. And also the solvent, I see that when it is with toluene, which is maybe the polarity is quite similar. So then the interaction between them could happen. But then with the heptane, like I said, that it's very sharp. So this actually the basic rule of this like and dissolve like. Still, can be applied in this to explain this. Why it happened, or other interaction maybe like in very molecular in small that really interference the homolumo like you show earlier. Just wonder because you deal with the what you call this homogeneous phase of the solvent catalyst and also the reactants. Just wondering.
You probably saw you got me thinking. Actually, I think we might want to just look at it from two slightly different perspectives.
Yeah.
The first one would be that in terms of the HOMO-LUMO energies, I think the same principle is theirs. If you have a solvent that doesn't interact strongly with your metal, they're going to be more well defined. But that will define your electronic transition, okay, and how broad the electronic transition is. I think with the infrared, it's more about how you're interacting with the molecules as they stretch out, or the atoms as they stretch out. That's probably going to affect the frequency. It does broadly. I'm going to be a little bit careful here, because normally the low dielectric constants you tend to see sharper bands, but actually I don't think that's true across the board, because dichloromethane gives reasonably sharp spectra, sharper than toluene, for example. Toluene's got a lower dielectric constant than DCM. So yeah, it's probably quite complicated. I mean, I rule
it's not really simple as that.
Heptane always gives brilliant spectra. And we've always assigned that down to this real lack of interaction between the heptane and cyclohexane is the same. You know, hydrocarbon solvents behave in that sort.
Okay. One last question from me, because it's really interesting. Yeah, because this is for the complex. I know this may be like out of topic, but then the transition state, I mean, the transition compound, the intermediate, I always see that it is like more in it attack the ligand that is in axial position, like in Z position.
Yeah, that's correct.
Have you seen others that like attack, like it's like, I think it is far from the one that want to be attacked, but then I think it's like more free, like on the plane on the plane side. But have you seen that or not yet? Mostly the successful one is in the axial one.
So I don't know if you can tell I'm kind of twitching at that question, because it's a really good question. And there's a lot of, we've given that a huge amount of thought, because it's a really important issue. So first things first, I think what we know for sure is that we make this isomer. Okay, because what you're mentioning is that the acetonitrile could go here or here.
Yeah.
And because if the acetonitrile was here and the CO was here, this infrared spectrum would look very, very different. So we know for a fact that we've made this coordination geometry, because we have this sharp and broad band in the spectrum. That we know. Okay. The question then comes, I think, is why? Okay, and we've never ever got any evidence for the isomer that you were talking about there, and it could come down to a couple of things. One is that we selectively lose one of these carbonyl ligands, one of the two trans-carbonyl ligands, and then the solvent binds. Okay. The other possibility is that we lose a random CO, and then it forms this afterwards. Because what we've also done, the calculations tell us this is the thermodynamically more stable isomer compared to the other ones. And the reason is that when you have three COs that assist to each other, you maximize the pi back bonding to them. Because if you've got two that are trans, they share the same metal d orbit, two d orbitals, and they're then it means that they get less pi acceptance. So this is definitely the thermodynamically preferred one. But what I can't tell you whether this one is formed straight away and it's the only thing that's formed, or is the CO loss random and then it rearranges in less than a picosecond to get that. I can't tell you. We just don't have the data to do that. And it would be very, very difficult to do, because the fastest you can go with this technique is probably 2 or 3 picoseconds. Yeah, and
picosecond is extremely fast.
It is.
Extremely fast.
There's always more. It's like pulling string. The faster you look, the more you find. It's
Okay. Right. Okay. It's very, very, very interesting. Yeah, because when we, to be honest, when we teach about this, I don't teach homogeneous catalyst, but in our third year we have this transition metal and coordination complex. Yeah, something like that. Yeah, and then yeah, sometimes we when we explain about this ligand, the position, and then how it is the active one and the no active one, it is we have just to explain them about the position, but in this case then we can see that yeah, when we have in, for example, an axial position, then we can observe them. Then that one is the active one compared to the one that, yeah, like you said, that if we can't see even in 2 picoseconds, then probably, yeah, it's not going to happen. Yeah.
And I think the one thing I would add is that when we've studied these reactions thermally at 100 degrees as well in completely different studies, actually in those cases it looks like again we get the same arrangement of the carbonyls. So having this facial coordination of the 3 carbonyls is definitely important, I think, to what's going on.
Yeah, that's true. Okay, well, is there any question from the students? Again,
Maybe Zulkarnain chat,
Oh.
the chat box. Do you?
Okay, let's see again. Okay. If there's no, I think
Something like
yeah.
a request.
But yeah, I don't. Zulkarnain, what year you are? Are you UE students or? Yeah, because he said that he wished that he could continue study in York University.
Okay.
Yeah,
Well,
after graduate. Yes.
ask him to send me. My email is Jason. Sorry, I'll put my email up. If
I
anybody
have the email address. Yeah, I got it from university address. Yeah, I got this your email address again.
Yeah.
Okay.
But feel free to pass that on. I'll chat to anybody about, because we have scholarships and things like that if people want to come and study. So
yeah, that's very, very nice to know. Yeah, because I graduated myself from UK university, so I really enjoy to live in UK for even though only 3 years. So, but yeah, apart from the weather, yeah,
I was about to say
everything is beautiful.
It's cold.
Apart from the weather, because it's always raining, especially in northeast, in northeast of Scotland. Yeah, it's always raining and gloomy, but other than that, it's wonderful. Okay, then if there's no question, I believe that students just like grabs from our discussion. Yeah, probably we should give more introduction before. Like, oh yeah, this actually is like more advanced techniques, but based on infrared spectroscopy, and then what we expect to see. Yeah, now after our discussion, I think the student can hopefully know actually what is the importance of this research. Yeah. Okay.
And as I said, it's leaving the scholarships and the visiting side. If students or anybody's got questions about the presentation, I'm more than happy for them to email me, and I will respond. And
okay, we will organize that, Bu Amina, and then we will send it to you.
More than happy to help.
About this question. Okay, then I think it's already almost 5:30 here.
Oh, 10:30.
So it's almost evening, 10:30 there. So I think I please give a round of applause again to Professor Jason Lynam for his wonderful talk, and I return this back to Bu Ami or Pak Asep, Pak Asep, to close this talk.
Okay, thank you.
Okay, thank you, Jason. Yeah. Nice to have your talk again. Yeah.
No, thank you all very much. Yes, yeah.
Asep, before this, we will have photo session.
Yeah, photo
Not
session.
yet. Yes, please.
Foto
I'm
session,
ready.
please. Sama siapa?
Okay, okay.
Sama
I
saya.
can take. I can take the photo.
Ambilkan ya. Satu.
Yeah. Okay. Okay, please everybody open the camera for a while. Let's Bu Tuti, Prof. Bakri, Pak Ridwan, please open. Pak Iman. Okay, Arnia, Fatia, Evan. Why I have to call everybody here to open the camera? Ibu Wayan, ya, Ibu in Bali, Bu. Ya, Bu Wayan is in Bali. Pak Subeki, well, which one is Zulkarnain? I want to see him. Ayo, Zulkarnain. Okay. Pak Bowo, ready? Okay. Yeah, everybody's here already. Mbak Pratiwi, Evan, why you didn't open your camera? Mbak Lisna. Okay, deh. Yeah. Okay, who will take the picture?
Saya, Bu.
Safira ya. Okay.
Iya.
Ya.
Oke.
Kasih
Baik.
Ababa ya, so we keep
Iya.
smiling. We have 2 pages. If in
Iya.
my computer we have 2 pages.
Ya, baik, Bu. Untuk semuanya, mari kita foto ya bersama. Let's take a picture together. Please open your camera and show your best smile. 1, 2, 3.
Manganese.
Manganese.
Nice.
Okay, for the first page. And the second page. Smile. Okay, thank you very much.
Thank you very much. Okay. Okay. Thank you again, Jason. Yeah. for the
Thank you all.
nice
Thank
talk.
you all
Yeah.
very much. Yes, I really appreciate the opportunity to come speak, and thank you for all the great questions. It was really good, really stimulating. Yeah, great. Thank you.
Okay.
Thank
Yeah.
you, Jason. Yeah, bye-bye.
Bye.
Bye,
Sehat-sehat Pak
everybody.
Bakri. Yeah.
Yeah, bye.
Kedinginan Pak Bakri nih.
Iya.
Yeah, it's very cold now.
-9 degree.
Minus 9
In
degrees.
my garden. Yes.
Right, yeah. I've been to York. It's a nice place, so everybody would come to see Jason there.
Well,
It's
Very
nice
nice.
city and nice university.
Nice.
Okay, see you, Jason. Yeah,
great.
bye-bye.
Goodbye, everybody.
Bye-bye.
Thank you.
Thank you
Bye.
semuanya.
Thank you.
I'm leaving now.
Everyone. Kita pernah.
Ya. Ditutup
Yuni.
aja kali, tutup aja. Bert.
Bu
Ya.
Yuni, terima kasih Bu Yuni.